Okay, so today we're going to be talking about momentum and impulse, and then going on to force time graphs, which is, I know, what we did kind of at the end of term. And then we're going to lead that into all the different momentum situations. And then once we've completed all the different momentum situations, then we're done. Basically, this is going to just be a lot of practice. It's a lot of kind of maths. So I think this is the easiest way to do it. If I kind of take you through a few things, and then you guys go and try some questions. So we're going to start off with Newton's second law. So we're going to start off with F equals M times A. Okay, so knowing Newton's second law can lead us into momentum. So we know another equation for acceleration, and that is change of velocity over time. Had a total mind blank. Change of velocity over time. If I then substitute that in, we end up with F equals M delta V over T. This is, or leads us to our equation of momentum. Okay, because we know, we've already spotted, we've already spoken about that this is our equation for momentum. You know that from GCSE, momentum given the symbol P equals M times V. Okay, so we know that that is momentum, and we're now able to link that into force. And we can see how an object's momentum affects the force of its change in velocity, basically. So if that velocity is changing, which is why we have that delta symbol in there, there is going to be a force experienced. Okay, so we can obviously use this equation just in its form like this. We could be asked what the force is, could be asked to rearrange it and find out what the change in velocity of the object is. But there's also other important things about this equation. So one of the key things is this time. So we threw exit sheets, and we looked at how if we increase a time taken for the collision, then that F is going to go down, which makes sense with the maths. So if this number goes up, this number is going to go down, provided these two stay constant. Okay, and so I can rearrange this equation as well to make impulse. So impulse is literally defined as force times time, or mass times delta V, so they're equal to each other. So it's equal to the change in momentum, not just the momentum. Okay, so impulse is the change in momentum, and that is linked through that equation. So we can therefore work out the impulse of a force. Okay, and using this T here, we know if we can get that T down, then we can get that impulse down, and that force will come down as well. So that is our very important equation. You will just have to get used to rearranging it, get used to using it, possibly getting used to talking about the relationships that the equation suggests. Okay, so talking about using the maths to explain how if I decrease the time, the force is going to increase. If I increase the time, the force is going to decrease. So we want to make that T as big as possible. Okay, and there are all kinds of applications for this. Okay, your seatbelt in your car is used to increase the time taken for your collision. That elasticity in your seatbelt just gives you a few milliseconds more of time. But if I can even double that T, I'm halving that F, provided these two stay constant. Okay, so children's play parks as well, they will have soft kind of cushiony. So there's anything where you're kind of being cushioned, a car's crumple zone, even things like carpet and things like that, anything that's going to kind of cushion something, so somebody catching a cricket ball and cushioning it, all those things are going to decrease that force in an attempt to possibly save a person's life, or just to reduce that force that somebody's feeling. Okay, so that then leads on to force time graphs. Okay, so I can find out quite a lot of information from a force time graph. Okay, so let's say, I don't know, let's just say it goes like that. I don't know why it's not starting at 0, but hey ho. So that's our force time graph. I can find out a lot of information from that by using the equation we just had. Okay, so if I just put it, F equals M delta V over T. So from that force time graph, I can actually find the mass of the object, or I can find the change in velocity, provided I'm given kind of one of the other two. Obviously, I can also find the momentum. So if I change this as Ft equals m delta v, I can find the change in momentum, or if it, let's say the object stops, I can find what its initial momentum was, and then possibly find what its initial velocity was as well, because I know its final velocity will be 0. Okay, so I can actually find the momentum, because this is equal to our change in momentum. So I can find the momentum of the body by this force time graph if I find the area underneath the graph, force times time. Now, there is no easy way for this, and I know you're all going to roll your eyes when I say that you are literally going to be needing to count squares. I know you don't like doing it. I know there are other methods in maths, A-level maths that you've learnt. You don't know the equation for the line, so you can't do any kind of differentiation, integration, whatever it is that you do to find the area under. You can use the trapezium rule if you'd like. It's quite similar to counting squares, but also in the mark scheme, they will give you marks for counting squares. So the examiner will be looking for evidence that you have counted squares. Okay, so let's say I've got some graph paper. All you're going to do is find your whole squares. So anything that's pretty much a whole square, just count as a whole square. So I'm just going to start in the middle. That's 1, 2, 3, 4, 5. It's easiest to count them so you actually know. So 10, 11, wow, 13. That's probably going to be like that, isn't it? So 14, 15, 16, 17. Now I will just go and count the pretty much whole squares and ignore the pretty much non-existent things. So I'm going to count that as a whole square. 15, I'm going to count that, that was 17, 18. I'm going to count that as a whole square. Wow, counting has gone down the drain. 19. I'm obviously going to ignore that tiny bit in there. Then you just got to try and start making full squares. So obviously, actually this one's full square. I don't know why I haven't counted that. So 20, 21, and then you start making them. So I'm going to count that as 22. I'm going to count those as 23. I'm going to count that as 24. You might even include that, 24. Every 2 of these, so 25, 26, 27, maybe 27 and a half, something like that. Okay, but them seeing evidence that you have counted squares will get you the marks, and then they will give you a kind of lenience then, because they can see that you've done the method correctly. But if you have got no evidence of what you've done, they're not going to give you any lenience, or the mark scheme will not have lenience written in for any other methods. Okay, so then obviously you'd use the scale to find out what each square is worth, times that number by 27 and a half, and you've got the area under the graph, so we've got the force time. I can then, depending on what you're given in the question, find out the mass of the object, find out its change in velocity, find out, or we would know now, its change in momentum. Okay, so force time graphs, really, really useful. You could be asked to plot, you could be asked to describe what's happening here. Okay, so over time, our force is increasing, then decreasing. So you might want to think about what could this be? What situation could this be where I've got a force that's kind of increasing and then decreasing? That force goes back to 0. So in the end, there's no forces acting on that tool. An object with no forces acting on it at all, we know must either be at constant velocity or stationary. So you could bring in another one of Newton's laws there as well. Yeah, and then you just need to be able to describe how this is useful for car safety. Okay, you did a lot of car safety at GCSE. If you're finding you're struggling with the wordings of the questions or anything like that, you need to go back to your look at GCSE notes. There's some brilliant videos on YouTube actually about kind of car safety and how it links both into the GCSE and A-level physics specifications. So go and have a look at those. But they should be relatively easy for you to answer because you have already done them. Both at GCSE and A-level. Okay, so you could be asked, as I say, to work out the inbox. You could be asked to work out the change in momentum, which you must know is the same as the impulse. You could be asked to sketch these graphs of your own from situations and then link them into car safety.